Hi, super happy to be here. Thanks for having me. Just for context, I lead an R&D team inside our ServiceNow's AI research division. So for people who don't know ServiceNow, we're probably one of the world's largest software organizations. We produce software, workflow software for back-end teams, HR, SecOps, IT operations, risk management operations, used by organizations, the largest organizations in the world. And so we have a pretty good visibility into some of the challenges and early successes with deploying AI systems and agentic AI systems around the world. So you'd have to be sleeping if you didn't hear some of these data points, right? AI is exploding in usage around the world, not evenly, of course, and there are bumps in the road, but massive growth in adoption. Where we hear ChatGPT used by upwards of 200 million users on a weekly basis. That's probably stale data at this point, probably much higher. Stack Overflow reports that over half of professional developers using coding assistants on a daily basis. Again, I have a suspicion that that's underreported. McKinsey, this graph comes from a McKinsey report. Over about 80% of large organizations in their footprint are using AI in one of their core functions inside the organization, and a lot more are using it across multiple divisions. And you can see the hockey curve going up on each of those graphs because it's being deployed by more and more organizations deeper into the organization. Gartner predicts about a third of enterprise software is going to be in some level agentic within a couple of years. But of course, we know the threats, concerns, and disasters are also growing, right? I think this conference is probably growing in size as a result of that. The attack side, massively enabled by the sophistication of the tooling that's being developed just generally for AI systems. The complexity of what's being deployed, right? We're no longer just deploying single models and expecting that an input-output exchange is going to suffice for the system. We're stacking many, many more components around the edge. So threat surfaces are growing monumentally large, and we're starting to see the spill of come out into the public on a daily basis. Now we see problems arising, big threats sort of breaking through barriers and whatnot. So people are concerned. It's stalling adoption at some level. And it's like leaders are increasingly aware of this problem. So systems are changing, right? We're moving away from this classic early Gen AI pattern of input-output exchanges, where it was basically like a chat-like experience, where you put a prompt in, and you expected an output, and that was it. Like there was not much in the way of persisting memory, but you could gain some value out of those early systems. And because that was where we started, evaluation also started there. And so a lot of early benchmarks and approaches to evaluation focused on this pure, simple input-output exchange. And so you see benchmarks created where a bunch of inputs are lobbed at a system, and the expectation is that they produce some output directly in a single turn. Of course, systems have gotten dramatically more complex. The model is now just one little tiny bit inside a much larger architecture. Memory of different sorts is attached, context engineering systems. We've got tools that are available to agents. Those tools can go out and access information coming from knowledge bases, the open internet, real-time streams of data. So the environment is complex. Trajectories, right? That windy arrow I've got drawn there on the screen. Agents are moving and multi-turn, complex trajectories being influenced by their environment and everything. And so risks are growing, monumentally large in number, but they're also diversifying in type. We're moving away from risks where you can think that it was just the initial input, often from a user, but potentially from like a wider RAG system or something like that, where the threat could live. And so you could just look at the incoming prompt and look at the response from the model and see whether or not there was anything harmful therein, to a situation where memory can be poisoned, trajectories can be distorted, environments can be poisoned, tools themselves can be noxious, users can be noxious, but the user can be at the initial front door, can be at the side door. Things are getting extraordinarily complex. Risk landscapes are growing and diversifying. And so here's the big problem. I mean, that itself is a problem, obviously, but this is an equally big problem, that testing is not keeping pace at all with the increasing complexity of the landscape. A lot of testing remains focused on that front door. So by front door, what I mean here is the initial input that's coming into a system. Think of a house, right? The front door is where people normally come in. The side doors and all the other seams is where things like air and gas and other kinds of noxious things can get into in a building or a home. Same thing with a system. A lot of the testing, because of that initial build out of the input-output exchange, remains focused at that level. Even when people are deploying agents, they're so strapped for time and resources and comprehension that they're deploying benchmarks and evaluation suites that are focused on the initial exchange. And at best, what they're doing is seeing whether the end state of the agent is influenced by that initial input. But as I was just showing with the systems, like the seams are open all over the place. And so injections and threats and risks can be coming in, and fuzz can be coming in all sorts of interesting and meaningful ways from all these other seams. And testing just isn't keeping pace with that. A lot of testing, sorry for the arrow there, I didn't do my, a lot of testing remains stateless instead of stateful. So what that means, stateless testing is when you basically discount the influence of change in the world. You freeze memory, you freeze trajectory, and you're looking at inputs and outputs. So it doesn't necessarily have to mean only front door. It could be that it's tool-based exchanges or other things like that, but you're kind of, for simplicity reasons, you're just assuming that what happened in step 1 of a trajectory has no influence on step 5, because that's just a really complex problem to try and deal with from an evaluation perspective. And so you lapse back into the simple paradigm of stateless testing. The problem is that agents are stateful actors, and the world is a stateful thing. And so this change is happening, whether you like it or not. And agents can influence the world over the course of their trajectory and be influenced back from their world. Memory can build over steps, and eventually, over the course of multiple weak kinds of attacks or weak kinds of fuzzing, can have monumental consequences for an agent further down in its trajectory. So stateful testing is an absolute must. It's hard, and it's just not where we are today. Context unawareness. So this is another one where it's hard to build benchmarks. It's hard to build evaluation suites. And so people typically, teams building AI, will go out there in the public and find public benchmarks or other suites that other teams are using to evaluate their agents or their systems. And that offers a certain amount of comparability. Like, it's easy to go and talk to your leaders about having performed really well in a benchmark that your competitor also put their agent up against. The problem with this is that those benchmarks and those evaluation suites are almost to a T enormously ignorant of the specific risks that your system and your agent faces in the world. So I'm at a conference where people, where threat modeling is probably the bread and butter of what many of you have done for a long time, or it's been like in the air. But the reality is that for a lot of people building AI systems, they've never even heard of the concept of threat modeling. The idea of starting from the first principles of what your system is doing, what it looks like, what risks are there given your architecture, and the assets that are on display, and what people may be motivated to try and do from a security perspective, but also just from a pure functional perspective. Just isn't in the culture of how people do things. And so the bandwidth constraints lead people to leverage these public taxonomies. So the context unawareness means that people are running numbers and getting back signal on how good or bad or insecure or secure their systems are that actually are poorly reflective of the real risks that systems are being deployed into. And unsurprisingly, the generalization pattern is very poor. People think they're doing really well. They deploy out into the real world and all of a sudden encounter a world that looks dramatically different from the one that they evaluated it on. And finally, the security utility trade-off. When people are measuring things like security and safety, frequently they're doing it in isolation from functional utility testing. And that's a real problem, because you can get a sense for improving the security or safety of your system and not have a good visibility on whether you're damaging or degrading the usefulness of the system. And we see this very often. People will do functional testing over here, and then they'll go over and they'll do security testing, and they'll tweak things to try and make it more secure, not paying attention to how it may be degrading functional performance. And so that's a real problem. We need to move away from that kind of a paradigm. Okay, so here's what I'm going to do for the rest of the talk. It's three sections. Map, test, and promote. With map, we want to map that risk. We want to get in and understand what the system actually looks like. This is sort of like classic bread and butter threat modeling. What does it look like? Who are the users? What kind of permissions do they have? What maybe they may be motivated to do? And so on and so forth. And we're going to convert that into a test plan. We're actually going to do the testing, and we're going to stand it on 2 legs. Contextualize benchmarks. This is basically measuring the knowns in our system in a way that offers comparability across entities and across time. And we're going to leverage exploratory search. So red teaming, again, this is kind of like bread and butter for the security community, doing it for a long time. Not very bread and butter for the rest of the community that are actually building AI systems. But even for people who do red teaming, there's I think, a significant formalization and automation paradigm that needs to come into how we do that, and hooking it back into how we build our contextualized benchmarks that needs to happen. Because that black space outside of benchmarks is growing in size and diversity at a speed that's almost incomprehensible. And so the benchmarks are measuring less and less of the world that we want to push things out into. And then we promote. So this is that last phase where you move from discoveries in the test phase to promoting them into something like a regression suite or a benchmark. And the mechanics of how you do that is not obvious, because if you just take simple discoveries that you're finding and pass them into your benchmark, you could easily be overfitting to the specific bias of your rig that you're using to attack. Okay, so we'll talk a little bit about those challenges. Okay, first step, mapping. Threat modeling. So again, sorry if this is like basic for a lot of people in the room, but for a lot of people who are building AI, this stuff has like never come across their desk before. We want to be asking questions in 5 key areas. Outcomes. What do we want to happen? And what, if it did happen, would be particularly grave? Okay, including things that would be really rare to happen. This is a difficult thing for people to wrap their heads around, because a lot of evaluation happens at the aggregate or average level for teams pushing out systems. But the tail risks are some of the biggest risks, things that can occur infrequently but have such monumental significance that the gravity of them is much bigger than some lower risk things that happen more frequently. Architecture. What does it actually look like? What are you shipping? Yeah, that sounds like a pretty basic question, but it's shocking how often you go and talk to a team that's building and shipping something, get 2 different people in the room at different times and ask them what's actually being shipped, and people disagree with each other. So this is like, I have this long ago background of being an ethnographer, where you go to a place and you talk to people to try and suss out the informal structures that sort of animate and breathe life into a society, and that kind of structure social activity. It's the same thing here, where you go into a dev team that is shipping something highly technical and pretty confined, but where there's actually not a codified and common understanding of what's being shipped. So getting a handle on what's actually being shipped is key. Users and roles. Who are they? What can they do? What do they have permission to do? What can they unlock in a system if given the chance to do so? Surfaces. Beyond the actual components of your architecture, what do the ends of the tentacles of your octopus actually touch? Right? Is it a knowledge-based system? Is it a stream of emails or like security tickets or IT tickets? Is it the open internet? Do they literally have access to everything? What are all the vectors that can come in through the ends of those tentacles? And invariance. This is a little bit like outcomes, but slightly orthogonal. What are the things that you absolutely do not want to happen? Like, for example, do not ever give a refund unless the refund has been approved by persona X, or unless X process has been validated in the system. Okay, so once we have these things, now that tells us kind of like what are the pathways that may be open to people and who might be able to do what. Now we want to build the kinds of attacks that may come through all those vectors. The first thing is a practice of having your ear to the ground, knowing what the heck is, like, what are people talking about as like novel attacks, particularly salient attacks, when architectures are changing and systems are being deployed. Like what is successful, what's being reported, what's getting past walls, what's coming up, what's coming out of the research. Basically, you just have this hungry vacuum of knowledge to build a knowledge base around attack types. And from there, prioritizing. So taking your threat model, taking what you know about the library, the vast library or catalog of attack types, and merging these things to try and come up with where the particularly important and salient attack types are that you want to take into account in your testing, and then distilling those into a package that's going to be ready for testing. So mechanisms, vectors, the knobs that you can turn to mutate things in an automated way if you wanted to, or I guess in a manual way as well. And your oracles. How do you know when an attack is successful or not successful? And then the test plan. So as I said, pairing risk and utility, absolutely central, so that we can understand the trade-offs between those 2 things. Fixing a budget of attempts and a stop rule. So rather than sort of like manually and informally going out and just testing all over the place and not recording how much attention you're spending in any dark corner of the forest. Actually creating some structure where you say things like, I'm going to say for every pathway, 200 attempts max, I'm going to record a discovery curve, and I'm going to report back on how the number of families that I'm discovering after so many attempts. And when that basically slows to zero, feeling free to actually have a stop rule that says that we're going to stop expending energy in this area and report that basically there's nothing left to find here, and we're going to move to another area of the darkness. There's always a risk that there are still things left, of course. But in the vastness of the forest, you have to be really careful about how you're spending that very limited resources that you have in testing. Stabilizing a sandbox. So for your tasks and your attacks, very often you're going to need artifacts. Things like a KB article or an incident or a web page or a banner on a web page. And so you want to pin those down, because every time that something runs through a benchmark, you want them to be using the same artifacts. Otherwise, you lose all comparability across runs and across entities that are running through the same benchmark. So you need to stabilize the sandbox so that you can have genuinely comparable tests. Target the coverage. So going back to your threat model, being very aware of how many big burning fires there are, where they are, and what your test plan is actually going to cover, at what depth, and where you're going to ignore. Almost certainly you're going to have to ignore some areas because you just don't have the bandwidth and resources to cover them all. It's just being really clear about which ones you're picking and which ones are left unexplored, and that gap has to be really clear for everyone. And finally, metrics and reporting. So thinking in advance about what the metrics are that you want to be reporting on, developing a template in advance. So that could include things like your attack success rate alongside your task success rate, severity mix, time to exploit at certain percentiles of the distribution, detectability, what happens before and after if I'm inserting like a guardrail or a defense layer, things like that. And so it could look like something like this. This is obviously a highly summarized version, but for an executive or someone, a decision maker, this may be what the only thing they're really going to look at. So your ASR, TSR mix, this is attack success rate and a task success rate. Like an attack success rate of 8%, down from 30 percentage points the previous time that you did this, whereas your task success rate almost unchanged at 86%. Gives people a longitudinal sense, but also a sort of like sense of the balance, whether that's the right balance to be having. The severity mix of the 8% that you're finding, how much of them are in high, medium, and low severity incidents? Time to exploit at the 50th and 90th percentile, like three turns versus 11 turns. These are just examples, but gives you an idea of like the kind of summary, high-level, high-quality, structured information that can be useful coming out of a run for decision makers. Okay, and now we haven't tested anything yet. Now we actually need to get to the testing. Okay, dual track, as I mentioned. Context-aware benchmarks and exploratory search. So just quickly to summarize, the former is for testing the knowns and offering comparability, and the latter is for hunting in those dark corners. The latter is becoming dramatically and more important as the dark corners actually grow into the dark vastness, if you will. Like the complexity of these systems and all the unknowns and the sophistication of attackers means that those dark corners are probably where most of the energy should be focused. And then building a pipeline between these two so that you're bringing back value from exploratory search into your regression suites and contextually aware benchmarks. Which brings me to Doom Arena. Okay, so Doom Arena is an open source testing framework for security and safety testing of agents that we released open source from ServiceNow Research maybe 9 months ago or something. It is very different from a lot of the open source frameworks that are out there or closed source frameworks and benchmarks. It is flexible, extensible. It allows you to translate a very grounded threat model into really good testing and to connect your real agent and agent architecture, not a false sort of premise of like a reference architecture or something, in a real environment where your agent's going to be operating. And to do genuinely real testing and learn a lot about real risks. So caveat, what it is not may also be really important to you. It is not a benchmark, right? It is a shell that is flexible and that can be turned into amazing testing, but it is not an off-the-shelf benchmark. And so there's a good side to that, which means the good side is that you're going to test some real things and you're going to learn some real things. The downside for a lot of teams is that, I'm going to actually need to build benchmarks, okay? So I'm going to need a task benchmark and I'm going to need a threat benchmark. or set of suites or regression suites or whatever in order to animate this. So you benefit from relevance, but you have to do some of the extra work. So it's not out of the box, at least not today. We're trying to build more of an out-of-box experience as we expand this, but today it is really a flexible shell that allows you to do good work with knowledge that you have about your agents. So super high level, kind of like flow diagram here. You start with that threat model. That's the output of the first mapping process that I mentioned. The attack config, this is where Doom Arena comes into play. You're converting your list of attacks, with each of which has a success filter and an attackable component, leveraging this attack gateway, which is a sort of clean and crisp way of allowing Doom Arena to interact with your agent in your environment to connect with the agent, the environment, and the users and tools and everything. So there's arrows going everywhere here, in part because everything is influencing each other, but also because the seams are everywhere. You don't want to just be able to make the user malicious, because the environment, the tools, the memory, the agent itself, all of these things could potentially be poisoned or malicious. And so you want your seams to be open and for Doom Arena to be able to engage with them. Okay, just to look super quickly into some of the components. So a task, this is what you kind of got to bring to the table. You need those contexts and artifacts that I mentioned to pin them down. A task needs to have its accompanying documents or whatever it is that it's going to interact with. That could be like a KB article or an email or something like that, so that every time a system is run across that task, they're using the exact same content. That's going to offer the comparability. You need to know what an optimal outcome is, right? You don't just need to know that your agent should help with a refund. You need to know, in this case, if this user asks for this kind of refund, the optimal outcome is that they do not get the refund. Okay, they're basically golden labels on these things. Invariance, in this kind of an example that I just said, is there a case where an agent should not ever give a refund if it's above $200 or something like that? That needs to be stipulated really clearly. And then allowed tools and preconditions. What kind of tools is an agent going to be allowed to use, and what are the things that need to be true in order for it to use any one of those tools? So you're going to need to know all these things about each of your tasks to build that task benchmark. And then on the attack side, we're going to need to know the attackable component, basically what's the target of our weapon. The attack choice, what's the weapon that we're going to use, right? Of all the things that you know about these different kinds of attacks, what are we going to deploy? The success filter, that should be, not filer. The success filter, basically you need an oracle of some sort that's going to be able to tell you, did an attack hit its target? And then the attack implementation, this is how you move from one attack to another or potentially many attacks. And so it's going to be pulling the next payload. And what the logic is for that, it can be anything from just rerun the exact same test many, many times, the exact same prompt many times, or it could be to mutate it in some small way, or it could be a much more sophisticated mutator under the belly. And so we'll talk about that as well when we get into automated red teaming. And then a gateway. So the gateway is really just the thin wrapper that allows Doom Arena to interact with your environment and your agent. Okay, so super high level. Gateway, don't try and read all the details here, but gateway interacts with your attack config, which is calling the attacks. And that attack kind of, that attacks bucket, the A down there in the corner, basically covers whatever your generator is or your mutator. And it could be very simple. It could literally be a single prompt, or it could be 100,000 prompts that have been very sophisticatedly varied or mutated in a way that you want them to be. And launching them at whatever whatever is under C. And C could be a wide variety of things. So a couple of examples. Once you set things up, it's extraordinarily easy to actually convert a threat model into a new attack. So things are built in a very modular, flexible, extensible way once you've done that pre-work. One quick little caveat here from some experience. Your system, the way your agent and your agentic framework is built is going to structure what kind of testing is possible. Just because you have an agent and it's acting in an environment doesn't mean it's actually going to be easy to test that thing. The extent to which the seams have been opened up for injection, not because they're they're protected very well, but it's just because people have not thought of this in advance. How easy is it for you to inject in seams? And then how well does your agent or your system evidence what it's doing? Is it leaving breadcrumbs? Is it leaving audit trails? These things are going to have a heavy influence on how easy it is for you to use this kind of framework or any kind of a framework to test your real agent. So homework to be done with your engineering team in the design phase, that just because they're building something and it works out there in the real world doesn't mean it's actually going to be easy for you to test that thing to know whether it's high quality or insecure or unsafe. Okay, some research that we did using Doom Arena on some public agents that were out there, and that's been published in a paper that you can all find. So the paper is all available for free online. Quick orientation on this table. So far left column, these are basically threat vectors or threat models. You'll see malicious user, malicious catalog, and then some combination type attacks. The first set of rows is for an agent in an airline use case, and the second half, or the bottom half of the table, is for an agent in a retail use case. We don't need to go into the details. You'll see the models. We're actually testing a few different types of models here, and then the next column is defenses. We had a guardrail that we tested presence and absence. What kind of an impact did it have? And then ASR and TSR, attack success rate and task success rate, measured side by side. Okay, one of the first things that you'll notice if you look, there's a lot of information on this table, I realize, but if you look closely and you read the paper, is that threat model dominates outcomes. Yes, it's true that switching model for model and defense present or not present does have some impacts, but threat model matters enormously. So if you start at the top in the first colored column on the far left there, you'll notice that you do have some high-ish attack success rates, but in general, compared to the lower part of the table, where the reds and the oranges start to show up, much less. Okay, and so that's basically moving down through a few different threat models, if you will, like simplified threat models. And indirectly, the message there is, well, I mean, it matters enormously. The extent to which you're going to realize your agent is secure or insecure matters enormously on whether you're actually capturing the right threat models in the modeling stage. If you'd stopped at the malicious user in this case, you'd have a very different read than if you had stopped at the combined threat model at the bottom, right? So that's extraordinarily important, and it's often lost in AI system testing, where people focus a lot more on, oh, if I switch this model for that model, oh, if I if I put a guardrail in front of it or something like that, and forget about the fact that actually the threat model is what drives the quality of the testing and the quality of the risk discovery in most cases. Second, guardrails do help, but definitely not fully, and they can massively damage utility, in this case anyway. So if you look at the column where it's like defense, yes and no, kind of third column over or something, and just pick say the row, GPT-4o row in the retail, so kind of like right smack in the middle of the middle row, you'll notice that the absence of a guardrail there, in the absence of a guardrail, attack success rate was at like close to 35%, and the presence 2%. So it had a massive positive impact on actually detecting and blocking those attacks. But if you cycle over to task success when the attack was present, so like the third colored column over, almost 40% task success when there were no guardrail present, and all the way down to lower than 10% when the guardrail was present. So just a really quick example of how measuring these things side by side can really reveal the trade-offs present in increasing security and damaging utility. And it's not obvious what the right decision is here on proceeding, but stakeholders need to have that information side by side to judge whether any improvement in security is actually worth it, right? Because a useless tool is simply not going to be deployed. It doesn't matter if it's secure or not. Okay, and then to exploratory search. So just to come back to this diagram, this is that thing that I mentioned sort of covers a lot. Lots hidden under the hood here. Your generator can live underneath this. This is the box where we're deciding what's the next attack to serve up into the system. Quick high-level sketch of a pipeline. A lot of this looks pretty similar to how things work when you're not using automated exploratory testing, with the exception of the mutator and then this arrow that kind of cycles back. So you're starting with a seed, and that seed could be expert human generated. It could be coming from some public list. It could be coming from some previous red teaming you had inside the company. That mutator is going to turn that into, it's going to fan it out into, could be hundreds, could be thousands, it could be a lot more different variations of that. What logic it uses to mutate is very much up to you, right? You have a lot of knobs at your disposal to figure out how you're going to mutate and which part of the dark space you want to explore. We've tested and experimented with lots of different things there. You execute, you judge, okay? You're generating so many mutations that you need automated AI-powered judging to help you, and then clustering and learning to avoid situations where you're finding all sorts of successful attacks that are all actually in the exact same area. They technically are different, but they're all in the same area. They're all part of the same family. You want to be sort of like greedily searching throughout space to identify as many families as possible. And then bringing that back and having it influence how your mutator selects where to mutate to optimally explore the space. Yeah. So this is from a different paper that we didn't publish, but I think is a helpful kind of example. Automated red teaming paper called rainbow teaming. The bottom, basically the x-axis of this grid here is like attack styles, things like misspellings, tone, role-playing, things like that. And then the y-axis is threat models, effectively, or threat areas. And so they built a system where it would basically, the mutator would kind of hunt through the matrix space and transmute, take something from this cell and transmute the style to this other attack threat model over here, leveraging the same style, and kind of forcibly move from cell to cell so that you didn't get stuck in any cell, which I thought was pretty interesting. We're not using this exact methodology internally, but it gives you a kind of idea of how you need to think about using automation and exploration to make sure you don't get locked in like hill climbing on small hills, and you're actually looking for the biggest mountains you can find. Again, this is a point I made earlier, but like focusing on exploit families as opposed to just individual discoveries, and discovery curves for exploit families. So what does this mean? The science of trying to move from a bunch of individual discoveries to clusters or families, and families representing some like basically a pattern, and that pattern being something that you could represent in a benchmark or in a defense suite, and not over-indexing on the individual brittle discoveries, which are real discoveries of successes, but nevertheless they represent just one little tiny needle drop in what is probably a larger whole, and what you're trying to characterize is the larger whole there. And then discovery curves is really just making sure that you're logging like how quickly does it fall off. If you're exploring a space and you're finding successes, and then all of a sudden it's slowing, that curve is actually a really important bit of information for decision makers, right? Like it's going to help you. If it never actually slows, that's probably evidence that you've hit a pretty monumentally large hole. But if you're able to find successes really easily and then it flattens really quickly, then that's going to give you a very different kind of signal. Okay, so come back to this. That's the same thing I showed earlier, the sample report. And what you absolutely need in addition to that report is this list of exploit families with minimal producers, because that's going to be useful for thinking about how to convert findings from an individual exploratory search or red teaming effort into something that is like a maintainable asset and could potentially be added to your regression suite or your evaluation suite, and eventually to a defense layer. Okay, so what we're looking for here is converting those exploit families into those patternized test assets that I talked about. And pattern card is kind of what you're looking at. This is where we're using natural language to describe what exactly is this attack, what is the vector that's typically used, what are the knobs of variation that might be used eventually when you build the generator, success filter or oracle attached to it, and so on. Then you've got to code up or build a template for your generator. You want to move that from a single example or a single pattern into something that can fan out into tens, thousands examples. And you could eventually add to your regression suite. And the pattern suite is what you would generate using your generator to eventually add to this your evaluation suite. And overfitting is like a massive danger here. If you're basically just taking the individual attacks that you found, imagine it's like misspellings or special characters or you name it, and promoting that directly into your evaluation suite. What the big danger is that what you're doing is you're going to be over-indexing on any biases in the rig that you're using to generate your attacks. Those are real discoveries, real successes, but nevertheless, the rig that you have, the model, the way you've architected that system, is going to have biases, because all systems do have biases. And if you use the direct output of that and put it into your evaluation suite, there's going to be a tight learning loop that happens here. Okay, and that learning loop is going to tell you a lot. The evaluation suite is going to learn to predict and defend against this rig, but it's going to be poorly generalizable to the world outside. Okay, and what you're looking for in evaluation suite is indication of how well things will do when you productionize, and so you want that to be more representative or indicative of performance in the wild than of any bias in your rig that generates the attacks. So you want to separate the methods. Actually, use 2 separate rigs. So, and you want a porous communication between them. You do want your attack rig to be sending information about what it's finding. What we're going to do is we're sending that information over in the form of pattern cards. Okay, and so you're in natural language describing the set of attacks or the family that you've discovered, which is very different from just sending over the actual examples of what you've discovered. You're kind of abstracting, creating some sort of description of the larger whole that you think you found, and the pattern suite, so 50 to 100 things that have been generated using your generator, which is different from the generator that you use to generate the mutations inside your automated red teaming tool. That's going to be sent over, and then that's going to join your benchmark. And so the rigs are actually separate. And from there, we want data separation, like in a lot of classic evaluation and machine learning and statistics. We want to isolate the seed data from what's used in the development and like iterative testing on a daily basis from the holdout or secret data sets that we use to eventually test when we think we've got something. We want, as much as possible, to keep that secret data set completely protected. No one's allowed to look at it, except very, very few people. Why? Because the more people know about it, the more that they'll try to develop in a way that will optimize for performance on that secret data set. You want that secret data set to be a good indication of how things will perform in the wild. And just like they don't have easy access to the world in the wild, we want that to be secret. And at most, they can test maybe once a week or once every X number of days, but they're not allowed to sort of like go back and forth and kind of like indirectly learn what the secret data set is. And then we're checking for generalizability, of course. Okay, so those are the three big steps. I think this is important, the accordion principle. So lots of teams look at this and they say, awesome, we don't have any resources, we can't do this. Okay, so what do we do? And I think my approach, I like the accordion principle here. The accordion principle is, accordions that can be stretched or they can be contracted. Nevertheless, no matter whether they're contracted or stretched, they're always still the accordion, they're the full instrument. So rather than saying, we don't have bandwidth, we have to do something, we're gonna use these public benchmarks. Don't do that, because these things are very poorly reflective of your actual risk profile. It's better to start small. You could spend a half a day in threat model, generate a bunch of high quality like pathways and attack types, and spin up a really loose automation or mutation, come up with a test data set that reflects your actual threat model that you can run your agent through without doing a whole lot of engineering or requiring a lot of effort. That's like the really simple 101 way to do this. And at the very least, you're discovering some things that you can then convert into a standing, growing test suite. A much more advanced version of this is going to take a lot more effort and engineering effort and like applied research and whatnot to build good automations. But it's better to start small with the whole instrument, the contracted accordion, and build out to the full accordion, than to actually have a very perfect version of the keys on the side of the instrument, but you can't actually play any music with just the keys. There's no accordion, right? Okay, so just to summarize, test your system, not the internet's understanding of what risks are, because they're absolutely not going to be the same as yours. Formalize and expand massively exploratory search. It's going to become an increasingly important part of how we test agents, if it isn't already. Make sure you're measuring utility and risk together, and promote with care to avoid bitterness. You can also avoid bitterness, but to avoid brittleness. That's it. That's the brittle lesson. If anyone knows that, the bitter lesson in AI, well, this is the brittle lesson. Don't promote without care, because you're going to end up with evaluation suites that are brittle and will not reflect well the realities that your agent will face in the wild. Thank you.